Hello, everyone. I'm going to switch the language as well as the topic is about quantum. So my title is The Frenzy of Science or the New World. I'm hoping that at the end you agree that this is a new world that you should all be concerned with. So we are here because we are all loving the big data. We want to collect more data, find the correlation between the data, trade data, securitize data. Data is the oil of the new century. So the problem that we are all facing is that this, excuse me, the problem that we are facing is that this computing machine that is supposed to manipulate our data is reaching its limitation. The beloved Moore's law that has been perfectly predicting what's going on in the world so far up to 2020 has arrived to this limitation. And if you look at all the big industry, superconducting industry, they're all predicting that by 2025, we are at the limit of our Moore's law, which simply means that this dream machine to be dealing with massive data, securizing it and allowing us to manipulate everything that we are dreaming for is literally need to consume the energy of the whole world to be able to let it happen. And it's not so surprising. You can see it even with the blockchain that how much energy it's getting. So here's the limitation that I want to talk about, and I want to say, given that we are looking at beyond the frontier, how can we break this barrier? We're going to break this barrier but with the tiny little particles, which are our quantum. So instead of being limited to always dealing with our classical information, which is our beloved 0-1, which is the basis of the building block of our information processing, we can come now to the new domain, new brickwork that we have, which is quantum particles, which they are not necessarily limited to be 0 or 1. You can think of them as being in the vector space, and you can think of them in different physical encoding. You can think of in any way that you want, but mathematically, they are not limited to 0, 1. Or artificially saying that in all the popular science that it can be both 0, 1, and hence you have massive parallelism. But we're going to dig into this a little bit as long as it's possible to show you that indeed is a possibility to break this barrier that we are talking about. So very quickly, quantum information processing is a field that we have been super excited over the last 4 decades in the science and academic. And towards my talk, I'm saying that why is no longer is a matter of the academic field and why all of you here should be concerned with. But indeed is a field that exists now for over the 4 decades because it allows us to, instead of dealing with the classical mechanic, which is describing the information processing, you have quantum mechanics, which is precisely describe the laws of physics of how to deal with microscopic objects. And we are able to build the devices which is obeying these new laws of physics once we go from microscopic to the microscopic. So unity of quantum information, that magical bits that I was talking about, is a system that can be in both 0 and 1 and have any other 2 quantum system. And it's not science fiction, it actually exists. Any quantum system that you pick up, like electron, superconductor, photonic, etc., these are examples of it. For the rest of today, I'm going to give a crash course of quantum computing so we can follow all the examples that I want to show you. Everything that you have seen in the basic classical computing have a quantum analog. For bit, you have 0, 1. For qubit, you can have both 0 and 1. But the phenomena that it makes it so special and allows for me to talk about all this landscape of what can we do in this world is the things that are changing. Let's go quickly. When you observe a classical bit, when you're reading some information, you're not changing the information. In quantum world, when you observe a device, when you observe your data, when you want to read out from your data, you're changing your system. And in classical world, you can massively copy and recopy and restart, a manipulation of your data. In quantum, you cannot. You cannot copy a system precisely a part of it. And all of these things that sounds bizarre are the features that we're going to exploit to define a new application part of it. And now, and a string of the bits, usually you can concatenate it. There is nothing special. You have some notion of randomness. In quantum, we have this quantum correlation, which is some sort of weirdo telepathy at the distance, which is exactly, again, another phenomena that is basis of our application. So this is a very quick course of what quantum computer is, and for the sake of this lecture, we just want to think that it is possible to manipulate and in a completely controlled way, like a classical computer, how to deal with these quantum devices. That's the different change. it can perform different type of computation. It can, that I will give a particular example. And the most important part to give the punchline is that not only it gives opportunity in order to do faster and better computation, but it's also a new threat for our cybersecurity that we heard the whole day about it, that how important it is in the fintech. So I will give you an example on that. So why do I stand in here? Or you can ask Alan, why did they invited a quantum speaker to a fintech? Because the quantum era has started. Over the last 2 years, if you happen to follow the news, 2 key milestones happened in our field. First of all, the Google supremacy that you might have heard about it has been announced, means that there is a device. It is not the universal quantum computer that you can order on the Amazon yet, but it is a device that is able to perform some computation, some random computation that cannot be simulated classical. This was a big milestone for a long time because we have gone through the barrier that we do something that none of the classical supercomputer by massive cluster, etc., can classically simulate it. We can discuss about that exactly because it's a little bit of a PR, but indeed we have reached that era. And the other milestone that has been achieved is that it's not just about computation, it's about also communication. What is happening in the communication domain is that Chinese, by putting billions of money, they managed to send a single photon, which is the carrier of this magical quantum bit, from Vienna to Austria, and present an impossible hackable and impossibly unhackable communication conferencing. So we are talking about all the cybersecurity, all of this threat that exists, part of it, but using quantum communication. It's been, again, decade and decade that we knew in the laboratory, in the university, how to create such a unhackable communication scheme, but it has been presented, and it has been a live streaming during the 2018. So these 2 particular milestones has started the era of quantum technology, and if you go quickly seeing it, what's happening in the national level, in the industry level, in the startup domain, is a field that is, some people say it is the new blockchain of the world, in the sense that we are the hot people now, like there is so much energy, there is so much hype, there is so much things, but there is also fundamentally a lot of new opportunity there, because we have moved, we have shown that these devices exist and it can be going there. So, since we are in fintech, I just try to pick up some random example. I cannot give through all the details, that why some of these new opportunity and new milestone can be very relevant to fintech, So if you look at the fintech, so let's talk about the speed, which is coming with the computational capacity of these new devices, whatever the reason this capacity is. So in this domain of fintech, of course, the question of optimization is one of the key questions. Portfolio optimization, looking at any type of optimization is something that we always exploit. And now, of course, there is plenty of classical algorithm that want to do. So why we believe, and there has been plenty of article that has been coming up lately, that why quantum annealing, which you can think of it, is equivalent of classical annealing, why this quantum annealing could have magnificent superior power to our existing classical one. So the way to think of it is that when you, let me see if we can do this, probably not. So when you look at the classical annealing, and if you look at any optimization problem, you're always stuck in the local optimal. Whereas the quantum magical power, which is quantum tunneling, or the process that is underlying our particle physics computation, allow us to tunnel through this local optimal. This is a very abstract way of presenting, but this is exactly what has been demonstrated, for example, with the D-Wave startup, which is in Canada, that has been heavily investing and working and designing such quantum annealing, which indeed show that in some optimization problem, of course it depends on a particular problem that you want to have and what evolution you want to have, but indeed is the basis that why we can get speed up when we come to the particular question of optimization in this domain of fintech. Another problem that is very, very popular, we heard about how machine learning is the new thing that we want to use in fintech to allow us to look at data segmentation, looking at the pattern recognition on any various part of it. Why, again, we believe quantum machine learning, which is another new hype that come to the field, is better at this clusterization of the data. So one simple way to think of it, I said that very quickly, that the quantum bits, you can think of them as essentially doing computation with vector instead of doing computation with bits. And when you start your encoding your computation with vector, quantum computers are actually very, very good to doing with the linear operation and matrix multiplication. In fact, one of the key algorithms that started the field of quantum machine learning is a very fast algorithm to solve linear set of equations. And this set of applications that are, again, suitable for this particular problem, each time you need to sit down to see what is the problem, are the beginning of the field of quantum machine learning. Another way to look at it in this figurative way, that we always know that probabilistic algorithm is doing something better because we can explore the space faster. But the quantum, you can think of them as some sort of quantum probability, that they are negative. They can cancel each other because it's not classical probability. And that allow you, again, exploit this vector space that is representing your data, and yet has a negative interference, something that you cannot have classically. And in quantum, we know how to utilize this thing to achieve to the answer to the pattern that you want to find in an exponential faster. And last but not least, again, another domain of application that is heavily used in the finance is for the simulation of the market behavior, like Monte Carlo simulation. So again, quantum computers just happen to be very good in quantum sampling. And in fact, we have heavy set of theoretical results coming recently out that quantum devices are capable to sample from probability distribution that classically very hard to sample. So there are these distributions that we want to predict because it's the behavior of the market whatsoever, and quantum is very good in those sampling. And again, we have the example of the sampling. So this is a very, very rapid way of saying that there are some area, and if you're now looking around, like next week there is a BCG which is organizing the quantum quantum for finance. There are area that over the last few years that we have established, quantum is actually good for this particular set of problem. Of course, it's not for all the problem, but each time you need to look at it. In order to dig in a little bit, the immediate question that all of you say, and okay, fine, these are very nice set of example, but where we are, where is this quantum computer that I can run on it, and should I wait for another 20 years or 30 years? What is perspective, and when can I really use this one in order to integrate in my industry and in order to integrate of it? So this is a very nice picture by Rigetti, is one of the startup in this domain of hardware development, that it exactly give you perspective where we are. Where we are is something that is called NISQ, Noisy Intermediate Scale Quantum Computer, a fancy word that usually physicists come up with. Essentially, we are in the domain of bad quantum computer. We know how to build a quantum computer with 100 particles. It's noisy, it's not perfect. But the surprising thing is that most of these applications that I show you can still work with noisy. You heard a lot, noise is good in machine learning. Overfitting is not good necessary. So in fact, the noise that in these devices are not a barrier for a particular niche application that quantum computer is believed to be good. So we are at the area of the NISQ, and if you look at IBM has announced their roadmap of 1,000 qubit by 2023. So we will be for a while, for the next few years, but right now I'm talking about in this domain of NISQ, but that doesn't mean that they are useless. And that's why there's so many, startup that is popping up on software side that they're already trying to do matchmaking of the use cases. That is the pain point in various industry, and trying to translate and compile them over these devices. And of course, there is a clear also roadmap for having the universal error corrected, making sure these qubits are much, much better. And that's roadmap is also a matter of the, not necessarily breakthrough, but it is a clear path that we need to go. It's just a matter of the time saying it. So just to, again, making sure that you see that these elements, these devices are applicable today. And I pick up one of the particular use cases, again, in this Fintech, which is the synthetic data generation. So it has been studied that, classical, for example, restricted Boltzmann machine can be used in order that you have some sample, which, for example, in this particular example, we look at the currency exchange. You have some sample of the data from the last week of exchanging of your currency, and you want to, out of this sample, to produce much, much more sample that is predicting how the market is trying to behave, so that you can plug this thing for the actual machine learning. This is a particular use case, how really useful in the financial tech, is still to be explored even in the classical domain. But what I want to show that in this particular example, when we play, you can exactly plug quantum, and this quantum sampling that I was saying that quantum is good to sample is precisely the type of problem that we can run over our noisy, bad quantum computer, and we can show that it's actually working well. So in this particular one, very similar to restricted Boltzmann machine, which is some sort of neural network that is trying to do. You can do it with a quantum neural machine, if you like, that is a parameterized circuit. You try to train using the classical sample that we have and trying to produce more sample. And in this work, short story, we run it on the Rigetti, which is a hardware that is available on the cloud with 6 or 8 or 12 qubits. So these are still toy model, if you like. But even with the toy model, with this very simple data, we saw that actually quantum not only capture the same performance of classical, it actually do give a better accuracy. So it's a very encouraging. It's still like anything else in machine learning, is a try and error, but we are strongly believing that this actually can push and become like a little quantum factory for the synthetic data. How useful it is something to be exploited, and we have now a big collaboration with Standard Charter and Rigetti in UK, trying to actually push this to exploit, to see that how which we can improve the device, improve our algorithm, improve our compiling to actually push this forward. So this is the message of saying that this sort of application can be start playing with if people are interested currently. Now I'm going to change the gear, for the rest of the talk to go back. This is not just one aspect. This was the speed and the potential of use case that we can take from the computational capacity. But another thing that probably you also heard a lot, quantum is also a destructive technology. So there is an issue regarding security. Now I want to pass the message, it's not only destructive, but it's actually create opportunity. So simply put, now it is a common belief that the future internet is not just going to be the way exactly as we have imagining it. It's going to be a hybrid connection of the classical and quantum. As I saw, China is already completely connected their local land points using the quantum communication through the satellite. They are linking it the longer distance. So this emerging new quantum classical network is bringing completely new opportunity, and we have example of that, how the security, integrity of data, privacy and everything will be affected, and in fact using quantum can be improved. So just let's go quickly through that picture. So essentially the quantum cybersecurity, we talk a lot about cybersecurity, but the field of quantum cybersecurity, looking at on all the aspects, the improvement and progress in quantum technology can have an effect on it. Thinking about any IoT sensing, any communication, any sort of data address, etc., they will be all affected with the progress of the quantum technology. So in particular, you can look at this very quickly just to say that, because some people have these minimalistic things that yes, indeed, there is the factoring, which is RSA, which is the hard problem that we're using for all of our communication, and quantum computer that is supposed to break that one. It's maybe in 30 years. So I come back in 30 years to think about my quantum cybersecurity attack. And that would be the same catastrophe that we were hearing this morning. We cannot wait for that. And this is not the only type of effect of quantum cybersecurity in part of it. Indeed, if you're thinking about the world that the bad guy have quantum computer and all of us are limited to classical communication, we need to completely change an underlying hard problem. It cannot be anymore just the normal RSA, elliptic curve encryption, etc. We need to completely replace them with new hard problem that is even hard for quantum computer, and that's why there is a nice competition. But that's not the end of the story. In this cat and mouse attack between crypto and crypto analysis, the point is that all of our security definition, all of the usual way that the hacker would hack your classical system, now you have a quantum hacking, which can look at the data and it can look at the sampling of the data in a different way, a part of it. All of your proof technique that we usually have the building block of underlying of why I can plug this particular SSH into my system and everything goes through, those are also been affected and you need to be revisited because the complete mathematics of our underlying has changed. But the part that is a more optimistic world to see that, we are not limited that only the bad guy to have quantum computer. The good guy like us can also have some limited quantum communication, some sort of quantum attack, quantum devices. And in that domain, you are able to look at a completely new information theoretical secure gadget. You will have the very famous quantum key distribution, which was the basis of this secure teleconference that I was mentioning, that China demonstrated it, that they're opening up completely new way of looking at our communication. There will be efficiency, which is a bottleneck. If you look at all of our blockchain, mining, all of this stuff that is there, because it's very, very slow that we can do this. This efficiency can also come and can be affected, as well as novel functionality. There are some particular data, like medical data or ethical data, that you want to have everlasting security. You don't want to be, anybody to collect all of this data, and in 20 years when the devices has improved, then you can breaking it. In quantum, we are able to achieve something that is never before was able. I can provide everlasting security, means that if you don't attack them now, you can never break them anymore in future. And of course, in the far, far future, in another 20 or 30 years, we even have the quantum cloud. The same sort of issue that we were discussing, from the Zama, different infrastructure talking about. You can talk about the security of cloud to provide of the ultimate encryption, fully homomorphic encryption. We can achieve all of them also with the quantum in a completely new way with information security. So there is a lot of opportunity. There is a lot of possibility. I have only 3 minutes left, and I have 20 other slides as a typical scientist, but I will make you to go through it. So the state of art of the quantum, as I mentioned, is that it exists. That's another message that I want to again saying it. European Commission has put a huge amount of announcement you're using as part of quantum flagship, as a new flagship of H2020, that is quantum information, quantum internet, quantum information infrastructure, QIC, that is establishing exactly at the government level to establish these links. France is part of this, of course. And this is a 20 years program that, first is starting with the quantum communication, then you want to establish and connect the devices. And this is a huge opportunity for, again, industry to come now to get involved on how to integrate it. One of the use case study that I wanted to talk about, which I'm not going through the details of this thing, is going exactly like the example of the machine learning that I was showing, that there are pain points that we're trying to understand in collaboration with the end user and trying to find a quantum solution. One of the things out of a lot of interview comes is device identification. This device identification is such a painful that anywhere they are ready to consider any funky things from the puff, physical puff, or whatever hardware token, because you want to have, depending on what application you want to have, how do you device identification? And in particular, in this beast that I'm presenting, that is going to be quantum, classical, good guy, bad guy, they're all having access with this one. How do you know that the client who comes and wants to connect can be identified to a server? And how does the server can know that I'm talking to the right end user? Very quickly, one of the solutions that has been exploited and recently has been integrated to the Samsung is the physical unclonable functionality, PUF, which is something that is particularly used in order to define the e-wallet application for the cryptocurrency. So these things, which is a very nice solution that is part of it, it has its own vulnerability, which we heard about the cybersecurity. And this vulnerability is really come from the fact that if I make my space of this unclonable challenge response that I'm using for the identifying my device to be too small, then even classically can be break. If it make it too big, then how do I store that one? And this vulnerability is even more severe because if you look at the most popular puff that exist out there, they are called optical puff. They are based on the scattering glasses that you need to make sure that, I cannot reproduce the same scattering pattern, but they are quantum. And because they are quantum, they are vulnerable to the quantum. And this is exactly, again, another use case that we exploit, that we show that this sort of puff, you can exist now quantum machine learning, trying to sample from these devices, and you use the quantum in order to break the classical security of this puff. So short story short, the same way that we know in the classical where I can look at the exchange of the messages and try out of this exchange of messages to create and mimic to be the adversary, and hence fool the device that, yeah, indeed, I am who I am, and hence, make the currency exchange to go through. In fact, now, because of quantum, because I'm living in this linear space, I can exploit this space much better. So there is the attack, there is this analysis. These attacks are not like short factoring that, you need to wait 200 years for the quantum computer to come. It's something that you can implement right now. You can play with this thing. And of course, the good news is that we also have solution. So the quantum, it takes whatever you do with one hand, it gives it with the other hand. So now I can use my quantum communication, which I just briefly mentioned at the beginning. It is by nature unclonable. It's by nature cannot be copied. That it allows me to create now a quantum puff. That's the new use cases that we are exploiting of it. So it looks like this. It's very nice. You can send it. You can send the part. And the whole point is that the basis of our security has changed. This is maybe the only message that I like to take, that before, the security base is always based on down the line. Something is so believed to be hard because so many mathematicians have worked on it, and now hence it's secure. Now the game is changed. The basis is the laws of quantum mechanics, and so many physicists have tried to break a quantum mechanic, and it's been, survived for 100 years, so completely has changed it. So that's why the security is there. So of course you can have the device identification. They are not yet readily available to put in a Samsung phone, but there need to be challenges, as a perspective. Just to finish up on this, I want to say that this big, speech trying to just say that there is a huge potential between the cybersecurity and concern from cybersecurity between quantum, and hence we believe that this is no longer just an academic job. So I'm not just putting my hat off, being professor and trying to encourage a student. We actually believe in it, and we put our own money and set up a startup. And it's not just us. Many, many people are in this domain trying to make link between the pain point in cybersecurity and potential in quantum and go through it. And one of these potential that we saw that is indeed, in order to propose that everybody come and get integrated and be involved, the button is that, do we need to be China that need to have put so much money in order to have satellite communication, or can we have come up with a different solution, simpler solution that I can pitch to some small data center that indeed you can take involved, and with the simple infrastructure you can play with quantum if you like. And the solution, we believe we have this solution. We have a specific model for the communication. If it's like an intranet, if you remembered how the original link has been defined, the ring network has been defined when the ARPANET has been setting up, we have redeveloped the same thing. The chair lady has been standing, so I need to go through this thing fast. So indeed, it is possible with the chip, without necessarily completely going, beyond the capacity of an industry that is want to invest on it, to integrate the quantum and unlock new application in there. And I really want to just mention the one thing, that this is not a frenzy of science. I was really hoping that you can see that this is a new world, and the sooner you get involved, the sooner you understand that the threat and opportunity is serious, the better I think you can benefit from it. So I'll stop there. Thank you.
Thank you.